Hello everyone, my name is Schamberger and welcome to the talk A Power Side Channel Attack on the CCA2-Secure HQC KEM. This is joint work together with Julian Renner, Georg, Sigl and Antonia Wachter-Zeh. Let me give you a quick outline of the talk. I will start with a quick motivation. I will introduce Hamming Quasi-Cyclic HQC. I will go into details of published attacks against HQC, and I will describe the error correction used in HQC as it is the main attack target. Then I will describe our proposed power side channel attack by first stating the attack methodology using a decoding oracle, and then in a second step going to describe how to build such a decoding oracle through the power side channel for HQC. I'm going to give attack results and then conclude in the end. Large-scale quantum computers have a strong impact on public key cryptography. Therefore, NIST started the Postquantum cryptography standardization process, with first submissions in 2017. We're currently in the third round of the standardization process, where NIST hope that this review period will include more work on side-channel system implementations. This work is a step into this direction. Let me introduce you to Hamming Quasi-Cyclic, HQC. HQC is a CCA2-Secure KEM in the third round of the NIST contest. It's a code-based crypto system, and it has advantages over other code-based crypto systems. Its main advantage is that its security does not rely on hiding the structure of the used error-correcting code, in contrast to, for example, classic McAleese. HQC is based on the quasi-cyclic syndrome decoding problem, which is a well-understood problem in coding theory. As the name already said, HQC has a cyclic structure. Therefore, elements can be represented as polynomials in the ring f2 of x divided by x to the n minus 1. This means all polynomials can be represented as binary values of n-bit size. Let me introduce you to the public key inscription scheme of HQC. I will go into details of the encryption and decryption. For encryption as an input, we take our public key, which consists of the polynomials h and s, and of course our plain text, which is the message m. The output is the ciphertext polynomial u and v. The first two steps consist of sampling 3 random polynomials with a fixed Hamming weight defined by the parameter set. Then we calculate u using the knowledge of the public key h. And in the second step, we encode our message m through the error correction defined in the parameter set, and we add some form of error onto it. During the decryption, we use our secret key y, and of course our ciphertext input polynomials u and v, and the output will be our decoded message m. So we first construct v prime, which is v minus u times y, and then the resulting v prime is decoded and our message m will be retrieved. How does this work? This works because with the knowledge of y, we can reduce the amount of errors in v, and therefore our error correction is then again able to correctly decode our message m. If we don't know why, then the amount of errors is simply too high and the decoding process does not result in the correct message. As the title already said, this talk is about the KEM, the key exchange version of HQC. This is the case as the public key encryption version is vulnerable against chosen ciphertext attacks, which is for example shown in reference 2. Therefore, HQC uses a variant of the Fujisaki-Okamoto transformation to receive a CCA2-Secure KEM. This works in the following. We provide a ciphertext. For the decryption, this ciphertext will be decrypted to a message, and this message will then be re-encrypted again. If the re-encrypted message and the ciphertext is the same, this means that we have a valid ciphertext, and therefore we can release the message to the outside world. If not, then we indicate a fail. And therefore, an attacker cannot craft arbitrary ciphertexts and therefore learns information about the decryption process. Nevertheless, there are published attacks against HQC that still can retrieve information to this decryption process, by observing a timing side channel in the error correction used during the decryption. As fortunately this timing side channel has been resolved with a constant time decoder during the error correction, this work shows a power side channel attack against used error correction in HQC. What is the error correction in HQC? HQC uses a product code of a shortened BCH code C1 and a repetition code C2. How does this work? The encoding takes the message of size k and transfers it to a combined code word of size n1 times n2. First, we encode our message with the BCH code. This is simply done by multiplying the message with the generator matrix G1. And then each bit of our BCH code word is then encoded with the repetition code n2 times. For the decoding, this is simply the inverse process. So we take our combined code word and retrieve the message again. First, we decode the repetition code to get a BCH code word. And from that BCH code word, we perform decoding and get back the message of size k. Here you see a simple example where k equals 2, so we have a message of size 2, a combined BCH code word of size 7, and a repetition code of size 3. So how does the process work? We have our m of size k, which then gets encoded with the BCH code. So it's m and some error correction information of size n1, which is the size of the BCH code word. And this is then encoded with the repetition code. So each individual bit is then encoded into 3, is repeated 3 times as the repetition code size is 3. During decoding, our individual repetition code word chunks, which there are n1 of, those repetition code chunks are then decoded individually. So each of these colored boxes will be decoded to 1 bit of the BCH code word, and the decoding is done through majority decoding, meaning if there are more than or more or equal than n2 half Sigl ones in one repetition code word chunk, then the result will be a 1, otherwise it will be a 0. What is the attack target of HQC? Therefore, we have to again look at the decryption algorithm of HQC, and we can see here at this multiplication we are using the secret key polynomial y, which will be the attack target. So what are the properties of y? Y is an element of f2n, so it's of size n, and it has a Hamming weight of omega, and omega is small. Here, for example, for HQC 128, which is the smallest parameter set of HQC, with 128 bits of security, n is equal to 23,869 and an omega of 67. Therefore, there are only 67 ones in y, and therefore y is very sparse. So what are we doing now? We are setting u to the 1 element, and therefore we get a resulting v prime, which is equals to v minus y. What is now the task? The task now is to find v such that through the power side channel we're getting information about y. And what is the solution for this? The solution for this is to distinguish between a correct and faulty BCH input through the power side channel in form of a decoding oracle. In the following, I'm going to describe how to craft these different V's given a decoding oracle, and later in the talk I will describe how to craft such a decoding oracle for HQC. So again, the attack approach. We want to find the positions of ones in y, so the support of y. What is a solution? We craft v in a way that the decoding oracle allows us to gain information on y. And we propose a 2-step approach for this. First, we find the approximate support of y, also called the super support, which are the approximate locations of ones in Y. And using this information, we then can find the exact support of Y, therefore the exact positions of ones in Y, therefore we have a successful attack on the secret key. For the attack, it helps us that BCH decoding has the following properties. If the input to the BCH decoder has a Hamming weight of 0, this is the all 0 code word, and therefore it is a valid code word, BCH code word, and therefore no error has to be corrected. If the Hamming weight of the BCH input is 1, this never results in a valid code word, and therefore always an error has to be corrected. Again, if there is a single 1 in the BCH input, then always an error has to be corrected. So we're using these two properties to find the super support of Y. And we exploit the fact that the repetition decoder decodes each chunk of n2 bits V prime separately. Therefore, we can attack each chunk separately. How are we going to do this? We are exploiting that the repetition decoder uses majority decoding. So we set only one entry of V to the border of the repetition decoder to the seal of n2 half and set all the other repetition code words to 0. I'll give a quick example of the first chunk of Y0, given we have an N1 of 4 and an N2 of 3. So let's start with this example. We have 4 repetition code words of size 3. And this is our V, so we're setting N2 half, the seal of N2 half to 1. So if we have N2 3, means we have to set 2 ones, add 2 elements here to 1. So we set these 2 elements to 1. And as we said, U will be 1, we just have to subtract Y from V. So if V minus Y, or as we have XOR, it doesn't matter if it's minus or plus. So V XOR Y equals V prime. So if we XOR these two values, we get the following result. So these two cancel out, and this one will be transferred to here. And now we're decoding each chunk to repetition. We set majority coding. 1 is below the border of 2, so it will be decoded to 0, 0, 0, and 0. So the BCH input is 0, and we learned that the all 0 code word is a valid code word, so no error has to be corrected through the repetition decoder, to the BCH decoder, sorry. And let's assume a second example where we don't have a 1 at this position. So we have zeros here, and we add those 2 1s to the zeros here. We have 2 1s here. This is exactly the border, so this will be decoded to a 1. And the BCH input has a 1 in here, and which results in an error. So if we have a decoding oracle which tells us an error is corrected by the BCH decoder or not, if no error is corrected, we know that there has to be a 1 at this or this position. And if an error is corrected, we know that this and this position doesn't have a 1 in it. So the first property that we have to discuss in finding the super support of Y is that there is a dependency of the Hamming weight of the different repetition code chunks. So we simulated for 2 million different keys for the different parameter sets of HQC the percentage which have a maximum amount of 1 in each repetition code chunk, a maximum amount of 2, and a maximum amount of 3. And if we look at HQC 128 with a maximum amount of 2, we can already successfully attack 93.2% of all possible keys. We therefore opted to provide a method to attack a maximum number of 2, of a Hamming weight of 2, but our approach can be easily increased to a Hamming weight of 3 with the trade-off of an increasing amount of attack traces. So here you can see the 2 input patterns for V giving a maximum Hamming weight of 1 and a repetition code size of 31, which is the case for HQC 128. So as I said before, we set the amount of 1s to the border of the repetition decoder. So it's the Sigl of n2 half, which is 16. So in this case, we set 16 elements to 1, which is indicated in black here, and we set all the other bits to 0. The second pattern, we set these 16 locations to 1 and these to 0. Okay, if we now add a y, which has a 1 at, for example, the position 3 here, this position gets cancelled out, so we have only 15 ones in here, which will result in no error to be corrected with the BCH code. Here we have 16 plus 1, which will result in 17 ones, which will indicate an error corrected by the BCH decode. So if we know if a 1 is in this range here, we know we have no error corrected with this pattern and an error corrected with this pattern. If we, for example, would have an error corrected here and an error corrected here, we would know that in the whole repetition code word, there is no 1. If we want to attack a maximum Hamming weight of 2 for the same example, then we would need 4 additional patterns to check. If we then know the support, the approximate positions, we can now attack the exact support of y. Therefore, we can check the individual bits of the corresponding repetition code chunk separately. Assume this example for a Hamming weight of 1 and a support which indicates that our 1 in y has to be in the range from 0 to 14. So what we do, we again set 16 ones in each pattern, but we know here is no 1, so we can safely set all these here to a 1. And then we check each position individually till we are here at 14. And the pattern, which indicates no error, will indicate the position of a 1. This can be easily extended to attack a maximum Hamming weight of 2. So, as the patterns work with the knowledge of a decoding oracle, I'm going to now describe how to provide such a decoding oracle. And what we want to do again is, if we want to distinguish two power side channel measurements if an error is corrected by the BCH decoder. We use a template matching approach shown in Ttest 2020 by Ravi et al. So first we have to find points of interest with Ttest. In the second step, we generate templates for both classes. So is there an error corrected or not, based on the found points of interest. And then for each pattern, we measure an attack trace and we match these templates at this attack trace to the generated templates. And therefore we have an oracle. How to generate the input patterns for the Ttest and the template generation is shown in this table. If we want to have no error, we simply set both u and v to 0, and so we have no error indicated. And if we want to have an error corrected by the BCH code, we simply set u to 0, which eliminates the influence of y, and we set the first repetition code chunk of v to n2 half. Okay. As we set u to 0, we simply eliminate y, and therefore we can perform the Ttest and also the template generation directly on our attack target. Our experimental setup consists of power measurements on an CW308 UFO board with an STM32F415 microcontroller. It has an ARM Cortex-M4 core. We use a clock frequency of 10 MHz and a sampling frequency of 156.25 MHz. We attack the reference implementation of HQC, the round 2 submission version. So, the decoding oracle, the first step is finding the points of interest to the Ttest. And therefore we have to see what the implementation of the BCH decoder and the reference implementation. It first calculates the syndromes, then it calculates the error locator polynomial, and from this error locator polynomial it computes the roots. This here is the Ttest of 1000 measurements of the syndrome computation, and we indeed can see that there are some samples where the Ttest indicates that we can distinguish these two classes. But if we look at the t-test result of the error locator polynomial, we can see that the leakage is much higher, and therefore we take the computation of the error locator polynomial as our primary attack target. In the second step, we have the template generation. So we need to generate a template for both classes, so no error or an error, and the template generation is simply the computation of the mean of all traces for a given class at the found points of interest. Again, the template generation can be done directly in the target device as there's no dependency on Y. Here we can see the template for the class no error, and here we can see the template for the class with an error. In the third step, we perform template matching through the sum of squared differences. Therefore, an attack target, an attack trace is classified to a class with the lowest sum of squared differences. This means we use each sample of an attack trace and compare these sample to both templates and sum up the differences. The attack trace will be classified to the template with the lowest sum of squared differences. Using our decoding oracle, we successfully classified 20,000 traces with it. This allows a successful attack on the HQC 128 reference implementation. We require a minimum of 2 traces per template, but results shown in this presentation are done for 500 traces per class. In this table, you can see the required attack traces for a maximum Hamming weight of 1, for which we need approximately 2,500 traces. And if we allow a maximum Hamming weight of 2, less than 10,000 traces are needed. This brings me to the conclusion. We showed a power side channel attack on the HQC KEM, of which 93.2% of the possible keys of HQC 128 can be attacked. This, of course, can be increased with a trade-off of an additional attack traces. In the paper, we also proposed solution for sorts of special keys. We show a linear algebra solution for a key where the Hamming weight of this range is larger than 0. And we show a method to use partial information gathered through our attack to reduce the information set decoding problem, which is the basic problem HQC is based on. We showed practical attack results on an ARM Cortex-M4 with less than 10,000 traces. For future work, we plan research on countermeasures, and we plan to transfer our attack to other HQC instances with a combination of Henrik-Muller and Reed-Solomon codes. This brings me to the end of my talk. Thank you very much for your attention, and here are my contact details.